Hey team, Andre from High Performance Academy here. Welcome along to another one of our webinars. Today we are going to be diving into the world of crankshafts and what they're made of, the manufacturing processes, and what you need to consider or keep in mind when you are selecting crankshafts for a build. Making sure basically you're getting the right product, not wasting a bunch of money on something that's absolutely unnecessary for your application. We'll get into that shortly, but before we do that, just to bring you up to speed with what's been going on around HPA labs over the last couple of weeks. And to start with, we are running another one of our giveaways, and this one is for a set of wiring tools. So we'll just head across to my laptop screen for a moment. There's 9 days left to get your name into the draw for this, and what you're going to get with this, you'll get a set of Ideal Ergo Elite wire strippers. Those are the ones that we personally use here at HPA. You're also going to get a DMC GMT232, just to chuck a couple of numbers in there, splice tool, and you'll get the DMC AF8 crimp tool as well. These are pretty expensive as well, particularly that AF8 crimp tool, and this is what you need if you want to be working on mil-spec wiring harnesses in particular. There's no point shelling out decent money for high-end Autosport connectors only to be trying to crimp them with subpar tooling. So this is the stumbling block for a lot of people moving from the world of building club-level harnesses through to mil-spec or professional motorsport wiring harnesses. So along with that, we are also including our HPA VIP membership. So if you don't know what that is, that gives you access to every single course we already offer. You're also going to get lifetime membership to our forum and our webinars, and you're also going to get lifetime access for free to every single course that we produce and release in the future. So you will never pay for another course. That entire package valued at over $3,000 US. So you can head to the link that the team will chuck into the comments, into the chat, to get your name into the draw. Remember, absolutely free to get involved. We will ship this to your door if you are the winner, regardless whereabouts you are in the world, completely free of charge. There are a few other tasks you can complete to get yourself a few more entries into the draw. So if that sounds like a bit of you, if wiring is something you're interested in pursuing, jump on that package. It is an amazing deal. I'll just give you a bit of an update on what's been going on with our SR86. If you are a regular follower, you'll know that last time I talked about the fact that we'd had a pretty successful race meeting with the car, which is great. A couple little gremlins crept in there, but nothing serious. And mechanically, the engine at least was really, really good, really strong. So happy with that. And we wanted to do a systems check, basically run the car for an hour hard and just make sure that our cooling systems were keeping up with making sure everything stays cool. That was something that was a little bit of a concern. Our last race was only a 6-lap sprint race, or a series of 6-lap sprint races, and it's a little hard to really prove what's going to happen over 6 laps. Unfortunately, when we actually got to the track, found out just about as soon as I left the pits that something wasn't quite right. We were having problems with variability on the air-fuel ratio, and basically that manifested itself as a misfire, so had to abort the running pretty quickly. Obviously didn't want to do any damage, and as a little added bonus here, just something that does make fault finding these sorts of problems much easier is that we do have individual cylinder lambda on the car. We do have individual cylinder exhaust gas temperature. Often when you are experiencing a misfire, it can be difficult to actually know for sure which particular cylinder that problem is occurring on. And of course, the two ways that represents itself when you've got the data that we've got, when you've got a misfire, you're going to end up with one cylinder, or the cylinder that is misfiring, reading incredibly lean. So that's a red flag to look out for. You'll also see, because there's no combustion occurring in that cylinder, if you've got individual cylinder exhaust gas temperature sensors that are just outside of the header flange and the turbo manifold, you'll also obviously see the exhaust gas temperature drop. The EGT is a good way of monitoring this, but it is a little slower to respond. There's a bit more latency in the response time of those sensors compared to the likes of a O2 or Lambda sensor. So that's what we found, and it was obviously a case of figuring out what was causing this. We hadn't had any problems with this in our previous test, and it ultimately ended up coming down to debris in the fuel system, which is a little bit concerning considering we've gone through that fuel system and basically built it from scratch. So we needed to get to the bottom of where that came from. And what I'll do is I'll just show you, if we jump over to my laptop screen, I'll just show you this a reasonably complex fuel system, because here we've got the factory tank. So it's a saddle tank that goes over the drive shaft, not particularly uncommon, and it's made out of a plastic material. And basically on one side, we end up with the in-tank pump that's actually the other side. So in our case, let's just do this properly. This side here is what houses the normal pump, and the other side, which I had circled before, that basically has a siphon feed that pulls fuel across into the pump. Now, in our case, though, that wasn't enough, where this tank's only a 50-litre tank. Anyone who's pushing a Toyota 86 hard will also find problems with fuel surge once you get down below about a quarter of a tank with the factory system. It just isn't designed to work out on a racetrack where we can pull 1.3, 1.4 G lateral without too much trouble. So we'll turn this around. We needed to get some more fuel capacity in there, and to do this, without re-engineering the whole car, the quick and easy solution was to actually add a second fuel tank, which sits up in the boot area behind a firewall. It's not ideal, but it was the only real-time critical solution we could come up with. So what we've got here is these two basically feed back up to that secondary tank. We've got two because there's a feed and there's an air vent, so we have a fast fill system for this car for endurance racing, and it's just as important to be able to get air out of the tank as it is to get fuel into it. So that's why we've got those two. Basically those connect with lines back up to the secondary aluminium tank. Now what we found, though, when we went through the whole system was this is the filter sock or pickup for the in-tank pump. To just explain how that works, we've got the in-tank pump. We've actually got one each side of that saddle tank. Those both pump up to a radium surge tank that's mounted up in the boot area, and then we've got two in-tank high pressure pumps that then pump forward through fuel filters up to the fuel rail. So nothing particularly unusual there, but obviously a bit of debris on there, and it actually turned out to be aluminium filings or aluminium material, which is a little bit weird considering there wasn't really anything obvious that could cause this. So we've been going through it with a fine-tooth comb to try and figure out where this material's come from. And what we actually found when we disassembled the fuel tank, the factory tank, was the cause of this was from our radium surge tank. So I'll just get this under the overhead and we'll have a quick look at it. These little things, we've been running them in both our 86s for a while, and they actually are a really nice solution in terms of adding some anti-surge into the factory tank. So basically they have ball valves on two sides. So the idea with the ball valve is that will let the fuel slosh into the surge tank area, but it won't let it return out. So traps it around where the sock is that picks up the fuel. This sits in the tank and it's actually assembled in the tank. Now, the problem we found, if I flip this over, is you can see there's been significant fretting between this and the plastic of the tank. I'll go over the solution in a moment. So when Jimmy in particular pulled this out, there were little pieces of aluminium filings essentially impregnated into the plastic underneath where that's been sitting. I'm not 100% sure why we're having issues with this car. We've had the radium in-tank surge tank system in our other 86 for about 4, maybe 5 years now, and we've seen nothing like this. However, this is a real issue. One of the potential sources of this issue with this car is that we have been also chasing a high-speed vibration in the car. So this sort of happens once we're in 5th gear and above, and I can't be 100% sure of this. I'm just wondering if that vibration is being transferred into the fuel tank. Obviously, it's going everywhere in the chassis, may be partially responsible for this. However, we needed a solution, and we obviously don't want to be having this problem again. So if we jump back to the overhead, what we can see, it's a little bit tricky, but Jimmy, our fabricator, or machinist and fabricator, has machined up these 4 little plastic buttons. So these are actually made out of a material called Delrin, which is very hard. It is designed for low wear, and those actually go through into the other side, and basically they've just been glued in there and also melted over so that they can't come out. So that obviously is going to stop that aluminium to plastic interface that we've been having that problem with. I should have probably shown you the other part of this. So this is the top part that goes into the factory tank. So it can support 2 pumps. We're only using one in the current situation, and basically that just locates positively in there, although as it turned out perhaps not positively enough. So we're expecting to have the car back together, that up and running in the next few days hopefully, and we'll basically just be monitoring the weather and see when we can get ourselves back to the track. So looking forward to at least getting an hour test under our belts and having a little bit of confidence, hopefully, that the car will be keeping cool. We've got the endurance series that didn't work out so well for us last year. That is coming up around about September this year. So we're hopeful that we're going to have a very well tested, thoroughly shaken down car that we can be confident we can go to the first round with a package that is at least going to get us to the start line, hopefully to the finish line. Honestly, couldn't care less if we see the podium or not. I'd just like to get a few finishes under our belt. Now, I just also wanted to mention a Instagram that I put up that got a lot of comments the other day. So if we go over to my laptop screen, this is a Nissan R34 GTR. We had the benefit of being able to work on. It's actually owned by a friend of ours that works locally here in Queenstown. And as with a lot of these cars, it's been developed over time with a few select upgrades. One of the things that the owner wanted to do was get an ECU into the car that provided it with a good quality, reliable tune, particularly the GTR series of cars. They're not getting any cheaper, and engine damage isn't something he was really looking forward to with an unknown tune. So we took out the existing Apexi Power FC and removed the mass airflow sensors that Nissan use in stock form and fitted an M-Tron KV8 ECU. So the problem is that for the most part, all aftermarket standalone ECUs use the speed density operating principle. So yes, there are a few ECUs that give us the opportunity to also use an airflow meter, but the majority work on the speed density principle, where they take input from a manifold absolute pressure sensor that monitors the pressure in the inlet plenum after the throttle body. And this works really well as long as you have a single throttle body and a plenum. It doesn't work that well though when you've got an engine fitted with individual throttle bodies, and it doesn't work that well with individual throttle bodies plus turbochargers, which is what we've got here on the RB26. So regardless whether you're running a naturally aspirated engine running ITBs or a combination like Nissan's RB26, and I'll admit the RB26 is relatively unique. I've only come across a handful of engines that use individual throttle bodies plus turbochargers from the factory, but Nissan liked it because they used that on the RB26, and also the N14 GTIR Pulsar with the SR20 had the same setup. Anyway, in stock form, absolutely fine because Nissan chose to use a mass airflow sensor. The mass airflow sensor, as its name implies, directly measures the mass of air entering the turbochargers and hence into the engine. So if the ECU knows how much air is entering the engine, it's pretty easy for it to do its job. When we get rid of those airflow meters in the aftermarket though, this is where a few problems creep in. If we, first of all, getting the signal for manifold absolute pressure in a individual throttle body engine is a little bit more difficult. We can't just take that pressure signal from one individual runner post throttle body. You're going to get massive fluctuations as the inlet valves open and close. That's not going to work. So the technique we use there is to use a balance bar. Fortunately, Nissan actually offer this in stock form, that basically takes a signal from each of the individual runners and basically gives us the average. Now, even if we've got that average signal though, it still doesn't give us a good load signal. It doesn't give us something that we can use as the load input for fuel and ignition timing. And if anyone's tried this before, what you'll find is that under wide open throttle conditions, everything's going to be seamless, but you'll face one of two issues, and it comes about at part throttle. Either you're going to get a situation where when you back off from full throttle, full boost, to part throttle, you're going to find that the engine runs incredibly rich. If you try and fix that, you'll face the other issue, which is where you try and go to full throttle from low load, you're going to end up with a massive lean area through the mid-range until you basically get up to full boost. And basically that's a compromise. You can't fix that with this standard speed density system. So I just wanted to just quickly go over this. We use the Mtron, as I mentioned, and they use what's called 4D mapping here, which is not very difficult. We've actually got a full worked example that we added on that exact car in our practical standalone tuning course for anyone who is interested in learning more. But basically, this is our main VE table here. And the axis, which would normally be manifold absolute pressure, is not very sort of descriptive, but this says efficiency calculation. We can define what that is, but in the case of this car, what we're using there is throttle position. So this axis here becomes the driver's throttle pedal position on 0 to 100%. So that's pretty much how we would set this up if it was a ITB, naturally aspirated engine, and job would be done. We'd use the same for our ignition timing. However, we've got the problem in this car that we could have wide open throttle at maybe 3 psi, we could have wide open throttle at 20 psi, our fuel requirements as well as our air fuel ratio targets, and definitely our ignition timing are going to be wildly dramatic. So how do we deal with this? We'll quickly head over to our ignition table, because this is really easy. Our ignition table is set up just like a conventional system. We just have manifold absolute pressure on that load axis, and this is because we need good control over the ignition timing versus the manifold pressure, or in other words, the boost pressure. So that's how our ignition timing works, really no different to any conventional turbocharged engine. So we head back over to our fuel. So we've got our main VE table, and this works in conjunction with another table here, which we'll go to, which is our lambda target table. So this is a volumetric efficiency based ECU. So this lambda target table is essential. And basically this defines for manifold pressure versus RPM, what air fuel ratio or lambda target we want the engine to be running. Interestingly, in this base map here from Mtron, this is actually a slightly unique load axis. They've used air mass final. So basically the mass of air entering the cylinder doesn't really matter. It's just another way of getting the right result. I would typically change this to manifold absolute pressure, because for most tuners it's just a little bit easier to look at that axis and understand where we're going to be running in it, rather than trying to figure out for yourself what the actual air mass per cylinder is going to be. But different way of getting around it. So basically, once we've got these, when we're at wide open throttle, the ECU is looking at the volumetric efficiency number, and then it's looking at whereabouts it's operating in this lambda target table, and that will allow it to manipulate the amount of fuel being delivered to the injectors in order to get the air fuel ratio where we want it to be. It sounds complex, but from a tuning perspective, it's really, really easy. All we do is start on this table and basically define the actual air fuel ratio targets we want the engine to run. Then what we do is we come back to our main fuel table. We start with the engine running on wastegate spring pressure, the minimum boost pressure we can get. And over the years, I've heard of tuners removing the wastegates entirely, wiring them open. We don't want to do any of that, completely unnecessary. Just start on minimum wastegate spring pressure, and we just tune this table exactly how we would tune any engine. Now, obviously, we're going to ultimately end up running up in this 100% throttle row, and we'll be doing our ramp runs, and we'll get our fueling dialed in. Once we've done that, this is where the nice part of the system comes in. We simply increase the boost pressure, and within reason, our air fuel ratio is just going to track our new target. And it's that simple. We can concentrate for the most part on our ignition timing. There is one little caveat to this though. Once we do start pushing the turbochargers really, really hard, and the exhaust back pressure does start to climb, at high boost and high RPM, we will start to see our air fuel ratio dip richer than our target. There's an easy way of cleaning that up though as well. We can use some compensation tables that will use manifold pressure as a load axis to fix that. Now you might be saying, well, that sounds like a lot of work. Why don't we just keep the mass airflow sensors? And fair enough. In some instances, mass airflow sensors actually do a really good job. In other instances though, particularly the stock RB26 mass airflow sensors are incredibly restrictive. And yes, there are larger Z32 airflow meters that people use once they step up the power requirements. But there are also problems with those in terms of atmospheric venting blow-off valves as well. The fact that most aftermarket standalone ECUs simply don't give us the option of a mass airflow sensor means that sooner or later you're probably going to have to get your head around this system. Again, if you do want to learn more about that, we do have a full worked example, and for our members as well, we do have another webinar you can search for in our archive, which actually covers the process of tuning this on an R32 GTR using a Link G4 Plus as well that you can watch. Righty, we'll move on. And next up, just a reminder about our podcast. If you've been hiding under a rock, we do now run a podcast. We release a new episode every week, and the latest episode is one that we shot, one that we recorded when we were over at Sydney Jamboree back in 2020, just before COVID broke out. So this is about a Toyota GT86 drag car that has been fitted with a relatively unusual engine combination, which is the 1FZ FE from Toyota. Big capacity Land Cruiser engine, not something that we'd normally associate with an engine that produces 2400 odd horsepower, but that's exactly what this does, 2500 in fact. So if you want to learn more about that and what makes it run, I think at the time it was the fastest radial import car in the world. Don't quote me on that. That was 18 odd months ago now. But yeah, if you want to learn more about that, you can search hpatechtalk.com or look for HPA Tech Talk on anything where you currently listen to podcasts. Getting on towards the end here, just talking about our latest video release, which came out today. Zach joined us to go over the process of branching wires out with your harnessing. And this is something that I know a lot of people sort of keep asking about when we run wiring webinars. How do we branch out our wires? And this is something we're going to be needing to do a lot, particularly if you're doing a concentrically twisted harness. This does require a little bit more thought around the process involved in terms of where your wires are in the different layers of your concentric twist. So free lesson there. Check that out on our YouTube channel. It is the latest video that has just gone live. If you've got any questions on that, please make sure that you ask those in the comments. We'll do our best to get back to you on those. If you like the video, please give us a thumbs up. If you haven't already subscribed, make sure you do so. And also, while you're at it, turn on notifications. That'll make sure that you don't miss out on any of our future video releases. All right, just a reminder again, we are running that giveaway for the Professional Wiring Tools Plus Training Courses package. 9 days left to run. Again, you can head to the link that the team have dropped in the chat to get your name into the draw. All right, give me a moment here. We'll get started with today's lesson.
If you like that video, make sure you give it a thumbs up. And if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.